okay, we have a function and we have a secant line, and we're going to turn that secant line into a tangent line by moving those 2 points close together. And so the action of that was kind of cool, and we could make movies, and the algebra of that was a big pain in the neck. Okay? I mean, if you really like algebra a lot, then it was cool. It was a lot of fun to do those homework problems. But if you weren't so keen on that, or you weren't so careful with your bookkeeping, then what you started with and expanded and simplified down, there's a lot of places where you could make some errors and things didn't turn out the way that you liked them. So for those of you who said, this is kind of cool, this algebra stuff, but I'm over it, today you get to celebrate. Because it turns out that most functions that we are interested in are more complicated than, for example, I think the one in your homework looks something like 4x, what was that one? X cubed minus 3x plus 5, right? The one on the turn-in assignment was 1 plus 4x minus 2x cubed. And so on your homework, most of you probably took up about half a page to calculate the derivative of this. Okay? And so this is not really that complicated of a function. So imagine when we start throwing square roots in there, and we start throwing trig functions in there, like sine and cosine, and we start throwing natural log in there, and e to the x. How are we going to deal with this limit definition, the limit as h approaches 0 of f of x plus h minus f of x all over h, and use that to calculate a derivative? Well, that's going to get pretty burdensome. So section 2.3 up through 2.5 are all about a bunch of differentiation rules. So rules to calculate derivatives that come from this limit definition, but we can shortcut this limit and use these rules instead. So 2.3 to 2.5 is all about differentiation rules. So today will be differentiation rules part 1. All right, now before we start talking about some of these rules and these formulas, I want to talk about some notation. In algebra, we have a bunch of different ways to talk about functions. For example, we might talk about a function by calling it f of x. Or we might talk about a function by calling it y. So f of x equals x squared, or y equals x cubed minus 3. And when we have the different types of names for our function, then the term for our derivative is also going to have a slightly different notation. So our derivative name for a function named f of x will be f prime of x. And that's the one that we've seen so far. Now, if your function is named y, then one way that we can call a derivative name is to call it y prime. And a second way is to write our derivative as dy over dx. Now, this notation here, this dy over dx, this is called Leibniz notation. And one thing you might notice about dy over dx is that the d looks an awful lot like maybe delta y over delta x, which is slope of a secant line is delta y over delta x. And if you shrink it down to 1 point, suddenly it's dy over dx. So it's got remnants of change in y over change in x in there. And if your function has no name, it's just some formula barfed onto the paper, well, then what we say is we're going to take the derivative of that stuff. So when I just write a d over dx, that without any parentheses behind it is written as, so d over dx means derivative of, and at this point, if I don't finish that sentence, if I don't have something behind the d over dx, if I don't have a question mark or I don't have some formula to put in there, this is an incomplete sentence. So you'll never see a d over dx sitting by itself out on the street just hanging out. Okay, d over dx is always derivative of something. So we've got derivative of blank because d over dx needs to have something to operate on. Okay, any questions about that notation?